Okay, so just to recap where we're at. So we're studying Graham-Smith orthogonalization process, or sometimes just called Graham-Smith process or algorithm. Okay, and it's about getting something called an orthonormal basis. So let me just recap what an orthonormal basis is. So orthonormal basis. Okay, so what is an orthonormal basis? Well, it's a basis that is also an orthonormal set. Okay, it's a basis that is also an orthonormal set. So what is an orthonormal set? So an orthonormal set of vectors, let's say u1, u2, u3, up to un, is given by, so in order for a set to be orthonormal, when you take the inner product of ui with uj, you get 0 if I and j are different. In other words, if you take the inner product with any two vectors that are different, you get 0. So they are all perpendicular or orthogonal to each other. If you take the inner product with the same vector, so u1 with u1, u2 with u2, and so on, you'll get 1. Okay, so that is the characterization of what an orthonormal set is. So it's a basis that satisfies this property. And Graham-Smith is the process by which we can construct such a basis. So let me just draw this diagram. Okay, so you have your Graham-Smith machine, and there's an input and an output. Now, the input to a Graham-Smith machine, you actually don't need a full basis for this machine. It is enough to just input a linearly independent set. So all we need for this input is, I think they were using V's. Let me just check that. Yeah, so we'll stick to what is written in the course notes. So our input are V's. Okay, and this set does not have to be a full basis. All it has to be is linearly independent. Right? Linearly independent set of vectors. And what this machine is going to do is going to output the same number of vectors. So for example, if you put a linearly independent set with 10 vectors in, you're going to get 10 vectors out. So W1, W2, up to Wn. So the index there is the same. And this set will also be linearly independent. But it will also be, so it's going to be linearly independent, but the original set was linearly independent to begin with. So what is so special about these W's is that it's not only linearly independent, it's also orthonormal. Okay, which is what we want. And you'll see when you look at the course notes that they in the statement of this theorem, they put something here at the end that the W's, yes, there's an orthonormal set, and they say that the span of the W's is the same as the span of the original set. So they say something like the span of this original set of vectors, v1, v2, up to vn, is the same as the span of these new vectors, w1, w2, up to wn. And what that means, so if, for example, you think of it as now you're putting in a basis, so linearly independent set or a basis, then the output will be a basis for the same vector space or the same subspace. In other words, you don't get a basis for something completely different. You get an orthonormal basis for the same thing, which is very important because what if it gave you an orthonormal set, but it's an orthonormal set for a completely different subspace or completely different vector space? Okay, so that's what this condition about the span is really saying, that you get a basis for exactly the same space. It spans the same subspace. Okay, so um, we'll go through the rough idea of it, and then we look at some examples. The reason why I'm taking my time with this is because this is a type of question that you usually see, if not on coursework, but on the final exam. And because the calculation is a bit long, it comes for a lot of marks. But the calculation, when you do like maybe 2 or 3 of these questions, you realize that the calculations is very easy, right? You don't have to differentiate anything. You don't really have to integrate anything. You're just taking inner products and adding. Okay, so it's a very easy way to get some marks. Okay, so what is the Graham-Smith process? Here's the outline for it, right? And these are from the slides. We'll go to the slides in a bit. I just want to talk it out first. So the outline of how we're going to do this is we're going to start with the V's. So we're going to start with these vectors, the VI's, right? And we're going to convert these vectors into a sort of intermediate vectors. That is what we will call the UIs. Okay, and what's so special with these UIs is that these U's, these will be perpendicular. So all these U's will be orthogonal. So we're going to take the V's and we're going to straighten them out first, right? And we get the orthogonal part, but we want an orthonormal. So orthonormal means orthogonal plus unit vector. So then once we get these orthogonal vectors, we're just going to convert them into unit vectors. And the unit vectors we call WI. And the unit WI is just the unit vector of UI, right? Which you'll know to calculate. It's just the vector UI divided by its length. And these will be the unit vectors. Okay, so first we're going to straighten it out, and then we're going to convert it into unit vectors. Okay, so how are we going to do that? So the process goes like this, right? So given it, again, we don't need a full basis. It's enough to just be linearly independent set. So given a linearly independent set, so we're given the V's, V1, this is one, V1, V2, V3, and so on, Vn. The first step is, well, according to this outline, we need to get the U1, okay? But since we're now starting, we don't really have anything else. We just pick the first vector in our list, and that would be U1. So we just take U1 to be equal to V1. Okay, because we're now starting, we don't have anything else to work with. So let's just take U1 to be equal to V1. So we don't have to straighten anything out because we just have one vector, right? So there's nothing to make perpendicular to this one vector. So we already have U1, and the next step is to get W1. Okay, and W1 is just a unit vector for U1. So that is just the vector U1 divided by its length. Okay, and I should say up here, what is the length? So remember, we are using this definition for the norm. So the norm of a vector U is the square root of the inner product of the vector with itself. Okay, so that's how to get the norm. Okay, so we have W1. Okay, I just check in the chat to see if there's anything there. Okay, good. So if you have any questions while you go, you could type it in the chat and I'll look at it. Okay, so we have uh, uh, W1, and now for the next set of steps, so now we need to get U2. Okay, so for the other UKs, so it's given like this. So for K equal 2, 3, and so on up to N, you're given this sort of complicated looking formula. It's not so complicated, that the U for that level is equal to the V at that level minus the summation as J goes from 1 to K minus 1 of the inner product of the V's with the W's. Um, or of this fixed V with this Wj. Okay, so in all of this, the V's are fixed, right? So we fix this V at that particular level, right? And what this part here is doing is this is something called the projection vector. So it's removing the projection of all of the W's that, I should say, it's removing the component of these W in the direction that V was in. So it's essentially removing the part of W1 that was in V. So let's say let's say it's V5 or something like that. Then that means I need to remove from V5 the components of W1, W2, W3, W4 that are in it, that are in its direction in order to get it to be orthogonal. Okay, so you don't need to cram off this complicated formula. We're just going to let's write out what is how to get U2, U3, U4, and so on, and you'll see the pattern. And once you know the pattern, you can write it out for any. Okay, so let's just say for K equal 2. So how do I get U2? I know U1, right? I know W1, right? I just calculated it up there. How do I get the next vector U? So U2, so U2 is just equal to V2, the second vector in your list, minus, so if J goes from 1 to K minus 1, if K is 2, K minus 1 is 1. So the second one is just one term in the summation. And it's just minus the inner product of V2. So the V's are always fixed. V2 so what you do is you subtract away the inner product of that fixed V vector, in this case it's V2, with all the other W's that you have already calculated. How many W's do I have so far? I only have one, W1. So I take the inner product of V2 with W1. That is going to give me a number, right? This inner product is a number. And I'm going to multiply that number by W1. Okay, and that will give me U2. And once I have U2, remember, we go from V to U to W. So what is W2? It's just U2 half, which is U2 over length of U2. Okay, so now I have W1 and I have W2. So let's write out what it looks like for U3. So for K equal 3. So let's see how to do it. So I want U3. So I'm going to take V3. So V3 is fixed. The third vector in my list, V3. I'm going to subtract from V3 the inner product of V3 with all the other W's that I have already calculated. How many W's do I have so far? I have W2 and I have W1. So in this summation, I have two terms. So I'm going to subtract away the inner product of W1 with this fixed vector, V3. So, okay, let me keep it It doesn't matter if I do W1 V3 or V3 W1 because we're working over the reals. So the inner product for us is symmetric, right? Remember the inner product for us, it doesn't matter if I do inner product of U with V, that's the same as V with U because our inner product is outputting a real number, okay? If it was output, if the output was a complex number, then then we couldn't do that. But for us, our output is a real number. Okay, so we're going to subtract from that V3 with W1, and I'm going to multiply this number by W1, and then I'm going to subtract as well V3 with how much W's do I have? Two of them. So I'm going to subtract V3 with W2 and scale it by W2. And that gives me U3. And once I have U3, I could get W3. W3 is just U3 hat, which is U3 divided by the length of U3. Okay, and so on. So that's how it is. So let's just write out so we can make sure we fully understand it. What is it for K4? Okay, so how many W's do I have? I have W1, W2, W3. So I have three W's so far. So for U4 now, U4 is equal to V4. So I'm fixed in V4. That is the fourth vector in my list. And I'm going to subtract from V4 the inner product of V4 with all other W's I have already. So subtract from it the inner product of V4 with how many W's do I have? W1, W2, W3. So I have W1 and I multiply that by W1. Then I subtract V4 from W2 and I scale that with W2. Then I subtract V4 from W3. Multiply that by W3. So 3 here. Okay, so you don't need to learn of that complicated formula with the summation and stuff. All you have to do is just know exactly what it is this whole algorithm is basically doing. Right, and of course, once you have U4, you then just convert it into a unit vector. So W4 is U4 hat, which is U4 divided by its length. Right, if you want to, you could put the underline by the vector. So you could do like U4 underline to show it's a vector, but you don't have to at this point, right? We know at this point what is a vector, what is a scalar. Yeah, so that's the Gram-Schmidt process. And when will the process terminate? It will terminate when you calculated the same number of W's as you have V's. So if the list you started with had 5 vectors, then you will stop at W5 once you hit W5. So you have to go one more. Okay. And you see that as you go on, as you calculate more of these U's, the calculation starts ramping up because you have to add a new term each time. And depending what's the inner product you're given, to get this inner product might take some time to calculate. For example, if you're dealing with polynomials, these inner products may be given by some integral of V4 with W2, and you need to integrate that. But if you are in Rn, so Euclidean space, this inner product will be the usual dot product. Okay. So if it's a usual dot product, that should be very easy. There's no integration or differentiation in that one. Okay, so now we could jump into the slide. Any questions so far on that explanation? I hope that was a bit clear, because once you understand that, the calculation is sort of straightforward. Um, Okay, so yeah, so this is what we just went through, the Gram-Schmidt process, and here was the equation we were writing out all the terms on. Yeah, all right. So the next one is, okay, so we could skip through all of this. This is what I drew out to begin with. Okay, so now let's look at these calculations. So there are more in the course notes for you to look at and try on. Um, there's more on your assignment that I just put up for you to try as well. Okay, so consider the linearly independent set, and you're given two vectors in R cube. Use the Gram-Schmidt process to find an orthonormal basis for the span of A, right? So the span of A essentially means A will form a basis for this space, the span of A. Because what is the definition of a basis? It's a linearly independent set. So A, you are told is linearly independent, and it spans the space. Now, if the space is the span of A, then obviously A spans the space because the space is the span. Okay, so A is a basis for this subspace. Remember, the span of a set is always a subspace. So A is a basis for this subspace. Okay, so essentially we're just going to use A and plug that into our Gram-Schmidt machine. Okay, so the calculation is we're going to label these vectors. So I'll label V1 as the first one and V2 as the second one, right? And according to the algorithm, then I need to calculate U1. So U1, we take equal to V1. And once we have U, we then convert it into W, which is the unit vector. So they didn't tell us what the inner product was, but we are in some Euclidean space. So the inner product you could take as the usual dot product. So U1 hat is just the vector U1 divided by its length. What is the length of a vector in Rn? It's just Pythagoras theorem. It's the square root of each of the components squared, of the sum of the components squared, right? So if this was just 2 dimensions, let me block this with my cursor, then it's just Pythagoras theorem. Okay, so you get as W1 this vector, 1 over root 30 by 152. Now, if you wanted to, I think I could write on this. Yeah. Yeah, so if you wanted to, you could multiply this inside by each one, and you could get it equal to like 1 over root 30, 5 over root 30, 2 over root 30 as the vector. Right, so this is the vector W1, if you wanted to. But you'll see when you're doing these calculations, oftentimes you get these thirds, these square roots and stuff, and it's usually easier to just leave the square root outside of the brackets, because it's usually just good to leave these scalars here, because when we calculate the inner product, you can move scalars out from the inner product. So this 1 over root 30, we're just going to move this out the inner product. Okay, and we don't have to worry too much about it. So that's a W1. So now we go on to U2. So U2 is V2, right? Minus, okay, what is this? All right. So U2 is V2 minus, and then you see here the dot product. So this was written like the inner product of V2 with W1, right? You take that, we're fixing V2, and then you subtract from it the inner product of V2 with all the W's you have before. We only have one W before. Yeah, and then you scale it by W1. So the inner product is the same as the dot product. Well, it's not the same, but the dot product is the inner product for Rn. Okay, so that's why you see they put a dot here. That's why they switch to the dot product. If you were doing this for like polynomials, then you can't, there's no dot product for polynomials. Then you need to do like the integral one. Okay. Okay, so this is V2 minus V2 dot with the vector W1 multiplied by the vector W1. And now remember that the scalar here and the scalar here, we can move out to the front. So I move 1 over root 30 out to the front, and this 1 over root 30, I move it out to the front. So I get 1 over root 30 multiplied by 1 over root 30, which is 1 over 30. Right, so that's why I said better to leave the square root outside because it simplifies a lot. And then you get 3 by 1, which is 3, 2 by 5, which is here, 2 by 2, which is here. Okay, multiply by this vector. So it's just 3 to 2 minus 17 on 30. So this, when you take this, the dot product of V2 with W1, you get 17 over 30, and then you scale it by W1. And when you work this out, you get this vector over here. So this is your U2. But we then need to convert this U2 into W2. And what is W? It's just the unit vector of the U, right? So it's 1 over, so I didn't want to put a 1 over, so I put to the minus 1. And it's just the square root of each of the component squared, and you add it up, right? And when you do that calculation, you get this as your vector. So this is your W2. So we stop because how many V's did we have? We only have V1 and V2. Therefore, I just need to calculate W1 and W2. W1, W2. So this set, and you could even check this if you have the time. Take the dot product of these two vectors, and you will see you will get 0, meaning that these two vectors are perpendicular to each other. Or, not or, but and, if you find the length of each of these vectors, you will get it to be 1. So it's orthonormal. It's an orthonormal set, and it's also an orthonormal basis for this space, the span of A. Okay, so as your first example, so what about this next one, where again, we're given a linearly independent set consisting of these 3 vectors, and we want to use Gram-Schmidt to get an orthonormal set or orthonormal basis. Okay, so again, label the vectors v1, v2, v3. Take u1 to be v1, which is 1, 0, 0, right? So w1, you don't need to do this calculation because obviously w1 is a unit vector, right? 1, 0, 0 is a unit vector. So w1 will be 1, 0, 0. There's nothing to normalize there. Okay, so we have w1. Then we move on to u2. So u2 is, remember how to get the u's. You fix the v's at that same level. So we have level 2. So fix v2, and we are going to subtract from v2 the inner product of v2 with all the w's that came before, that we already have. And again, we are in Rn. This is R cube. So the inner product is just the usual dot product. So this is just v2 dot w1, and we multiply that number by w1. Okay, so this is v2, 112, minus v2 dot w1 multiplied by w1. So this guy, I think, gives 1, 1 by 1, which is 1, plus 1 by 0 is 0, plus 2 by 0, 0. So this gives 1, 1 by 1, 0, 0 is 1, 0, 0. So u2 is just the vector 0, 1, 2. Okay, so now we need to convert it into a unit vector. So W2 is U2 divided by its length. So it's 1 squared plus 2 squared plus 0 squared, right? So there's a 0 squared in here, but I didn't put it, which is 1 over root 5 by 0, 1, 2. So this is your W2. And so you're not done yet because you started with 1, 2, 3 vectors. So we need to end with 3 vectors. So far, I have W1, I have W2. So we need to get W3. So we need U3, which is V3. And so this is the formula here. Again, you don't need to write this sort of formula. You can just write out what it is. So we are at level 3. Okay, so we fix V3 and we subtract from it the inner product. In this case, it's the dot product of V3 with all the W's that we have already worked out. So we subtract from it the inner product of V3 with W1 and multiply by W1. And we subtract from it V3 with W2 and multiply by W2. Okay. So you see at each level, the calculation starts ramping up because you have to do, at each level, you have to do one more inner product. And these inner products, if you look at it, each time it's like a new inner product you have to calculate because we then calculate this one and to get U2. To get U2, we have to take the inner product of V2 with W1, not V3 with W1. So each step you need to calculate one more inner product and they are all new inner products. So each step is like a bit more. Okay, so this is V3. V3 dot W1 multiplied by W1 minus V3 dot W2 multiplied by W2. Again, better to keep the roots outside because when we go to do this calculation, we can pull this stuff out. So this guy goes out and this guy goes out, and you get 1 over root 5 by 1 over root 5, which of course is 1 over 5. Right, that's this 1 over 5 you see out front. And this is just the dot product of these two vectors. And this guy is just the same vector, so this works out to be 3 over 5. And your vector, what is this, U3, works out to be this vector. And the final stage is we then need to normalize it. So we need to convert this vector into U3 hat. Okay, which is just U3 divided by its length, right? And the length of the vector is just square root of the inner product of U3 with itself. Since we are in Rn, that's just U3 divided by the square root of U3 dot U3. Okay, and U3 dot U3 is this. Well, this is 1 over it. Okay, it's the sum of the components squared plus 0 squared. Okay, so this is W3. So W3, W2, and W1. This is W1. This is W2. This is W3. Right? This forms an orthonormal basis for the span of A. Now, notice in this case that we have three vectors here, and we are in our cube. Okay, so therefore these 3 vectors will span a 3-dimensional space. So I know we didn't prove this, but you could look at the proof of it. That if you have a n, if you have a right? So I know we didn't prove it, but you could prove that if you have an n-dimensional subspace in an n-dimensional vector space, then the subspace is equal to the big vector space, right? So that's actually a proof. It's not something that's very straightforward. Okay, so in this case, we have 3 vectors here. They are 3 linearly independent vectors, so they will span a 3-dimensional space, right? This set here will span a three-dimensional space in R cube. So the three-dimensional space it spans is R cube. That's what the rest of it was saying. So in other words, these three vectors are an orthonormal basis for R cube, right? So R cube has a orthonormal basis, the standard basis 1, 0, 0. Right, so R cube already has like a standard basis. It's 1, 0, 0. Not standard, yeah, the standard basis, but an orthonormal basis 0, 1, 0, and 0, 0, 1. Right? These three vectors are all perpendicular to each other and they are all unit vectors. So this is an orthonormal basis for R cube. But what you see here is another orthonormal basis for R cube. So these orthonormal bases, they are not unique. Okay, so in this one, what if we have now polynomials, right? So the calculation is the same, it's just a bit more involved. So consider this the vector space P3. So this is the space of all polynomials of degree up to including 3. So we have the constants, the linear, the quadratic, and the cubic polynomials here with inner product. So rather than the usual inner product, they gave us this sort of funny inner product we find here, right? So we don't need to prove that this is an inner product. You can just take my word for it, right? So if I want to get the inner product of two vectors, I have to integrate this entire thing. So I need to differentiate each of them 2 times and multiply it together. And then I add on to that 2 times, and then I evaluate each of them at 0. And then I add on to that the evaluation of the polynomial at 1. Okay, and you are given this linearly independent subset, so 2 polynomials of P3, where P1 is 1 minus x squared and P2 is x minus x cubed. Right, so I want to convert this set into an orthonormal set. Okay, so anytime they say the word convert to orthonormal set, it's Gram-Schmidt. Okay, so like usual, I let U1 be the first vector in my list. So now instead of V's, you have P. Instead of V1, V2, you have P1, P2, right? But as long as you understand exactly what you're doing in the method, it doesn't matter what letters they use. So we take U1 to be the first vector, P1, right? And I need to normalize it. So I need to get the length of U1, right? I need to get U1 hat, so I need to get the length. By definition, the norm squared is the inner product of the vector with itself. So I need to work out what is the inner product using this equation of this polynomial. So where we see P and Q, you're subbing in the same polynomial, 1 minus x squared, into this entire thing. So it's the integral. Okay, so I see they already worked it out. So what is the second derivative of P1? So the first derivative is minus 2x, and the second derivative is 2. Sorry, minus 2. Right, so minus 2x plus, and if you evaluate P at 0, you get 1. So 1 squared plus, and if you evaluate P at 1, you get 0. You get 0 squared. So this is just the integral of 4 plus 2. Right? And the integral of 4 is just 4 times x, evaluated at 0 and 1 plus 2, so that's 6. In other words, the norm squared of this polynomial is 6. Therefore, the norm is root 6. Okay, so W1, my vector W1, is the vector U1 divided by its length, which is root 6. Okay, so this is my W1. And again, you can leave the square roots outside. Okay, so now to get U2, So even though we have a different letter here, if you remember how these formulas work, then it doesn't matter what letters they put, you should be able to write the equation for all the other U's. So remember, U2 means we are at level 2. So we're going to take the second one in our list, which is P2, right? And we're going to subtract from it the inner product of P2 with all the W's we have already found. Now we've only found one W, that's this guy. So we're going to subtract from it the inner product of P2 with W1 and multiply by W1. So I need to work out what this is, P2W1, this inner product, right? This is P2, and this is W1, and this is the formula for how to get the inner product between them. Okay, so the inner product between P2 and W1 is given by, so it's the second derivative of P2 multiplied by the second derivative of W1, so that would be this guy, so you'll just verify it, plus 2 times the evaluation of these at 1, plus 2 times the evaluation of these at 0. Okay, and that gives minus integral 0 to 1 of 2 root 6x. Okay, so you all could integrate this and you get minus root 6, right? Remember the inner product of two different vectors could be negative, right? If you put the same vector in, if it's the same vector in both components, then it cannot be negative. That means you did something wrong. But if you put, two different vectors and you get something negative, that could happen. Okay, so now we could go back to our formula. So U2, we are at level 2, means I'm using the second one on my list, which is P2. I'm going to subtract from it. P2, the inner product of P2 with all the W's I have before. So the inner product of P2 with W1, I'm going to multiply that by W1. Okay, so this is P2. Let me see if I can write this as well. Right, so this guy here is P2. This guy here was the inner product of P2 with W1. So that's what we just worked out here, right? And this guy here was W1, the polynomial W1 that we worked out. Okay, so simplify, and you get this polynomial, right? So this polynomial is U2, or you could say U2 of X. It doesn't matter if you do U2 or U2 of X, same thing. Okay, so we need to now convert this into U2 hat, right? Which is U2, which we have divided by its length. Okay, so now we come here and we work out what is the length squared, and then we'll square root the answer. So the length squared is the inner product of U2 with itself. So that is the integral of U2 by, I shouldn't put the dot there, anyway, U2 by U2, right? So this is U2 squared plus 2 times U2 evaluated at 1, U2 evaluated at 1, and this guy here is U2. I think the second one was evaluated at 0. Okay, so you get this plus 6. So I just said you all could integrate a quadratic polynomial. So integrated, evaluated at 0 and 1, plus 6, and this works out to be 10. So the length squared, norm U2 squared works out to be 10. Therefore, norm U2 is square root 10. Okay, so W2 is U2 divided by its length. So it's 1 over root 10 by U2, 1 over root 10, and this here was U2. Okay, so this is W2. And how many vectors did we start with? We started with 2 vectors, right? P1 and P2. So I have W1 and I now have W2. So I'm finished. So therefore, an orthonormal basis, right? An orthonormal basis for the span of that set B is the set containing W1 and W2. Right, so it's the same formula. The only thing that changed was the inner product that we were using. Okay, so yeah, so there's a bunch of different words for this stuff. Perpendicular, orthogonal, normal. Okay, any questions so far? So if you have any question, feel free to, you could unmute your mic and ask it, or you could type it in the chat. I'll look at it while I pull up the um, next topic. Okay, no questions? All right. So um the next set of topics, so that's the end of inner product spaces. So remember I told you that as we progress through this course, the material is actually going to get easier because the way this course is structured to be taught, they start with the abstract vector space stuff, and then they move towards the more concrete type of calculation based things. So pretty much everything else from here go forward, you all already know how to do. Okay, you all would have encountered it at high school or maybe in your first year courses. And it's all pretty much row reducing. So from here on up, from here on, it's essentially we're going to now deal with matrices and see how they enter the picture. Well, we already saw sort of how they enter the picture in when we were studying linear transformations. Remember that a linear transformation has a matrix representation of it. So linear transformations and matrices are actually the same object. Okay, so matrices are now going to enter our story. And the only thing I have to really teach you is, well, we have to go through a couple of proofs. And I just need to teach you the theory behind row reduction. But the actual calculation, I think everyone here, if I give them a matrix, they could row reduce it. So the actual calculation is just row reduction. Okay. So let me first sort of motivate, how matrices again enter into our story. Okay, so if we consider the map A, so usually we have a function f, but I want to use a letter E, right? So we have a map A, and it's taking something from Rn. So it's taking a string of n numbers, and it's outputting a string of m numbers. So how is it doing it? It's taking, so it's given by A of x. So this x consists of n numbers, and it's giving you A times x, where A is a m by n matrix. Okay, then I claim A is a linear transformation between these two spaces. So maybe I should um, write out what that is. Let me just write a little bit what exactly is that. Yeah, so they say you're given a map, call it A, so maybe I shouldn't have used A. Anyway, from Rn to Rm, okay? So what do vectors in Rn look like? Well, they look like a string of n numbers. So x1, x2, all the way up to xn. And what do vectors in Rm look like? So instead of x, I'll use y's, right? So y1, y2, all the way up to ym. Okay, so that's a string of these numbers. And we'll call this guy x. And we call this guy vector y. So this map is going to, this map A, different color, this map A is going to take in a vector in Rn, okay, and it's going to output a vector in Rm. So how is it taking in n numbers and outputting m numbers? What exactly is this map doing? So what if I told you that this map A is a matrix? So this is given by, so this here is a map or a function. And I know the confusing part. The confusing part is I'm using the same letter for the map as the same letter for the matrix, right? So this is sometimes often done in maths and it confuses a lot of people. I don't know why they insist on doing it, but well, they insist on doing it to show the link between the map and the matrix because they want to say that the map is the matrix, but it's not really the matrix. Anyway, so the map and the matrix are both given the letter E. So what I'm going to do is I'm going to take a matrix A, and this matrix is, I always forget this, so it's M by N. This is a M by N matrix, okay? And I'm going to M by N matrix, yeah. And I'm going to multiply it by the vector X. So technically it should have been X transpose. Anyway, so the vector X, I'm going to count this vector as being a n by 1 vector. Okay, n rows on one column. So this is my matrix, right? We have n columns and m rows. Right? This is my matrix A, and I'm multiplying it by this guy, which is my vector X. Put a little underline there, X, which is 1 column and n rows. And I know what y'all are thinking. You're saying, but hey, shouldn't it be the opposite? Doesn't it have 1 row and n column? And you're absolutely right. This does have 1 row and n column. Technically, I should have written this as r n by 1 instead of rn to show that it's a column of numbers. But what is the reason why I didn't write that is because Rn is isomorphic to Rn plus 1. So now we're just identifying the two spaces to be essentially the same space because they are isomorphic as vector spaces, right? The example for that is if I give you, for example, let's say 4, 7, minus 1. That's pretty much the same as if I write it 4, 7 minus 1, right? I am not really changing anything. I'm just choosing to write it a different way. That's the whole idea of isomorphism. It's pretty much the same thing. You're just writing it a different way. Okay. So yeah, technically it should be Rn by 1, but because these are isomorphic spaces, we can identify these two as being the same space. Okay. So this map A is basically taking a matrix, a m by n matrix, and multiplying it to the left of this vector. And of course, you all know how matrix multiplication works. It only works if these two numbers must be the same, right? And the answer, the size of the answer you get is this one, m by 1. Okay, so m rows and n columns. So you get this guy I'll call y. So this is m rows and 1 column. Okay, so what I was trying to explain here is that if you take a vector in Rn and you multiply it on the left by a matrix, by an m by n matrix, the output is a vector in Rm. So this map, left multiplication by a matrix of a suitable size, is a mapping between Rn and Rm. Not only that, you could show that this map is a linear transformation. Very easy. Let's do it. So take x1 and x2 be vectors in Rn, then what is A of x? x1 plus x2, right? So by definition, that is a matrix that I'm calling. I know the matrix is the same as the map. Just bear with me. I'm calling the matrix A. So maybe let me write the map in red. So the red will be the map, and the is it red here? Yeah. So the red one will denote the map, right? And so this is the matrix. So it's a matrix by x1 plus x2. And because this is a matrix, you know it will distribute over each one. So that's just A by x1 plus A by x2. And this guy here is just the map A applied to the vector x1 plus the map A applied to the vector x2. Okay, so that is the first property for linear transformation. And what's the second property? I then need to work out what is A by, so let's just say alpha be some real number. What is A by alpha x? Right, so by definition, that is the matrix A multiplying on the left by some scalar multiple of this vector x. And of course, you know, if you have like a matrix like 2, 1, 7, 3 multiplied by, let's say 4 into 1, 2. Of course, you know that this 4, you can move out here and then do the matrix multiplication and multiply the answer by 4. So same thing, I'm just moving the alpha out. This is alpha into AX, which is alpha. Maybe so. Yeah, so let me take off the brackets. Yeah, alpha by AX. AX means matrix multiplication. So this is alpha. AX is just the mapping A applied to the vector X. Okay, so what do we show there? Therefore, this mapping A is a linear transformation from Rn to Rm. So matrices are linear transformation, right? And what is the equation for that linear transformation? It's this, left multiplication by that matrix. Okay, so that's how matrices enter this picture. Matrices are linear transformations. This is the name of the transformation. This is how and it's acting on a vector, and this is the recipe for how to do the calculation. You take the matrix and you multiply it on the left by the vector. And what we just showed here is that this mapping, this type of map, is indeed a linear transformation. So every matrix is a linear transformation. And what we showed in the chapter on linear transformation is that every linear transformation between finite dimensional vector space has a matrix representation. Okay, so what we showed here is that every matrix is a linear transformation. What is the transformation? It's left multiplication by that matrix. And we also know that any linear transformation between, okay, so for us, we are always working with finite dimensional spaces, between finite dimensional vector spaces as a matrix representation. Okay. So therefore, linear transformations and matrices are the same thing. Right? So matrices and linear transformation are the same object. Because if I give you one of them, you could go to the next one. If I give you a linear transformation, you could find a matrix to represent it. If I give you a matrix, you could write it as a linear transformation. How do you write a matrix as a linear transformation? That's what we just did here. Take the matrix and left multiply it. That's a recipe to convert it into a linear transformation. This is just an aside. Maybe it's something you all will think about during the weekend. So it's usually we could draw a diagram like this. So V and W are finite dimensional vector space. So V and W are finite dimensional. Okay, I shouldn't write it right up. Let me write it. V and W are finite dimensional. So let's just say the dimension of V is n, and the dimension of W, let's just say, is m, right? If we have a linear transformation between them, let's say T is a linear transformation between V and W. Since V has dimension n, V is isomorphic to, let's say, Rn. And since W has dimension m, W is isomorphic to Rm. Right? So you could say isomorphic. Right? And what is the isomorphism map? It's the coordinate map. You take any vector in V, write it in terms of its basis, and then pull out its coordinates. That gives you n numbers. You take any vector in W, write it in terms of its m basis vectors, pull out the coordinates, that gives you m numbers. So these mappings are the coordinate maps, right? Isomorphic via the coordinate map, right? And I'll put here what it does. So if you take like any vector, A1 W1 plus A2 W2 plus AM WM, it maps this guy to A1, A2, AM. So this map is the isomorphism map that shows W is isomorphic to RM, and the map that shows V is isomorphic to Rn is similar map. You take A1 V1 plus A2 V2. So the V's and the W's are basis vectors. AN, VN, and I'm going to map that into n numbers. So I just take out the n numbers, A1, A2, N. Okay, so that's the isomorphism map. And now to go from Rn to Rm, I need a linear transformation that takes a vector from Rn to Rm. Do I know of any linear transformation that takes vectors from Rn into Rm? Wait, what did this thing do? Look, this transformation takes a vector from Rn into Rm, right? So matrix multiplication takes a vector in Rn to Rm. Okay, so so I can make a linear transformation from here into here. What could that linear transformation be? Well, it could be maybe I take a vector here and I multiply it on the left by some matrix, by M by N matrix. What would that matrix be? Anyone want to take a guess? I'll write it in the chat or maybe unmute your mic and take a guess and tell me what would this matrix be that would do this transformation for me? Is it a special matrix? No one wants to take a guess. Okay, no worries. It's a bit of a technical question. The matrix A, that will do is the matrix representation of the linear transformation T. So maybe I should have put a basis. So V basis given by, let's say, B V1 up to Vn. And this guy has basis given by, let's say, fancy C, W1 up to Wm. So this matrix that does the linear transformations between these two spaces is precisely the matrix representation of the original, linear transformation. Convert this linear transformation as a matrix with respect to these two bases. That is precisely the matrix that you see here. So it's B, C. Right? That does this mapping. So everything we did so far can be summarized by this diagram here. And mathematicians give diagrams like these a special name. They call this commutative diagram, or they say these arrow diagrams commute. Diagram commute. Diagram commute means you could go this way, then this way, or you could go this way, then this way, and you get the same answer. right? So if you're looking like at a more advanced book on linear algebra, they might put, something like this diagram for you. Okay, so essentially what this is saying is that this motivates why we are now using matrices, because up here I have the complicated abstract vector space with these abstract vectors, abstract linear transformation. I don't want to work with that stuff. I just want to work with nice matrix multiplication with vectors of n numbers. I want to work in this world. So this is saying no need to work in this abstract world. Bring everything down to the easy matrix multiplication world, and then lift the answer back up to the complex, to the more abstract world. Right? So we start with this abstract vector space stuff. We bring everything down to just matrices and do matrix multiplication, row reduction, whatever. Do all our calculation here, and then we lift the answer back up to get the correct result. Okay, so hopefully that side note um, helps put into perspective where the link in between all of this stuff. Okay, so let's jump back into presentation slides. Okay, right. So what I just explained there is written sort of by these points. Okay, so what is a system of linear equations? So oftentimes, when you're doing a calculation, you might have noticed that oftentimes your calculation boils down to solving systems simultaneously, solving simultaneous equations. And that is by no coincidence. That happens because what you were doing, you see those two different worlds that I showed you, the abstract world and then the calculation matrix world. What you were doing in those calculations was you were starting with something in the abstract vector space world, and you were bringing the calculation down into the matrix world. The calculation in the matrix world is precisely solving systems of linear equations. So it didn't happen by chance. It happened because that is the way, well, that's the way the whole linear algebra stuff is designed to work. Okay, so what is this system of linear equations? We essentially want to talk about this essentially brings in the theory behind any number of equations and any number of unknowns. So in high school, they would have taught you how to solve two equations and two unknowns. You solve it, I think, using substitution or elimination. Maybe later on, maybe they taught you how to solve three equations and three unknowns. What we're going to do is we're going to look at how to solve uh, m equations, in n unknowns, and m and n may not be the same. Okay, so let F be a field. A system of m linear equations and n unknowns is a set of linear equations of the form. So linear equations mean that the unknowns appear just like this, to the power of 1. They don't multiply each other. There's no sine, cosine, e to the x, anything like that. They look like this. So some number times the first unknown plus some number times the second one, and so on. So the index A11 by A1, A12 by X2, the first index that you see here tells you which equation you are on, right? So A21 tells you you are in the second equation. A2n, so 2 means you are on the second equation. AM something means you are on the nth equation, right? So the first index tells you which level you are on. The second index tells you which unknown or which variable, or we could say unknown, which unknown you are the coefficient of. So for example, A12, the first index is 1, means you are on level 1. the first equation. The second index is 2. It means this is the coefficient of x2. So AMN. The first index is m, which means you are on the m equation, which is the last equation, and you are the coefficient of the nth unknown, right? Another way you could think of it, what has two indices? A matrix. The entries in a matrix has two indices. So the first index, you could think of these equations as forming rows. You could think of the unknowns as forming columns. So the first index you could think of as a row number. The second index you could think of as a column number, right? Let me write that for you. So what I'm saying is Aij, the I you could think of as a row number, and the J you could think of as a column number. So that means this system, you could rewrite. So what we're going to do is we're going to rewrite this entire system as a matrix equation. So pull out all the constants, all these numbers, all the A's, take them out. And we're going to throw all of these A's into a matrix. And that is sometimes called, since all of these A's are coefficients, that is sometimes called the matrix of coefficients. Matrix or the coefficient matrix. Right, so that. The coefficient matrix. See, it contains all the coefficients. Right? And it's a m by n matrix. So f for us, you could take f as the real numbers. So this is our m by n. Okay, the unknowns, I have n of them. So I could take these unknowns and stack them as a column of n numbers, right? So these are the unknown vector, right? This is the unknown vector, and it's a, so again, you could take it as Rn by 1, or if you want to, you could simply say it's Rn because they are isomorphic. And the right-hand side, you could take all of that and put that as another column of numbers, right? This is sometimes called the right-hand side vector, or the forcing term if you're in physics, right? So physicists and engineers and stuff sometimes refer to this as the forcing vector or the forcing term. Or we could just say the right-hand side vector, right? So this entire system could be written in a nice compact form as simply the matrix A multiplied by this column vector X equal to another column vector B. Now notice that the vector X has n rows, right? N rows. The vector B has m rows, right? The matrix A, what is the size of A? It's a m by n matrix. What is the size of X? It's a n by 1. So these two must match up for matrix multiplication to work. And the answer is the remaining. It's the m by 1, which is B. Okay, so the system, a system of any number of linear equations in terms of any number of unknowns could be written in this compact, nice compact form, AX equal B. Yeah. In fact, many other linear algebra courses are designed completely around studying the system, AX equal B. So this is another way you could study linear algebra by studying this thing, AX equal B. When do they have solutions? How many solutions when it have solutions? What are the properties of this matrix A and so on. Okay, so some terminology. So in this system, AX equal B, you see if this right-hand side, so now X represents a column of unknowns and B represents a column of numbers, okay? If all of the numbers in B are 0, right? So if the vector B is just a list of zeros, so if the right-hand side is always zero, then this system is said to be a homogeneous system. So homogeneous means the right-hand side are all zeros. If any one of the terms in this vector B is different from zero, we say it is non-homogeneous. Okay, so AX equal B, like I said, is just a nice compact way to represent an entire system of linear equations. And you probably know how to solve a system of two or even three linear equations simultaneously. But what about a system of a million equation and million of unknowns? So this is what computers do all the time when they perform simulations or do graphics in those video games. Yeah, so how we have it written here, AX equal B. You see the X and the B have like lines underneath it. So most books you will see after they introduce this, they will then drop this bar. They will drop that on the bar and simply write AX equal B for convenience. So if you want to, you could keep the bar, but if you want to, you could drop it. I usually just drop the bars. Okay, so does the system have a solution? So if a linear system is said to be consistent if it has a solution. So one solution, two solution, infinite solution, doesn't matter. If it has a solution, we say it is consistent. If it does not have a solution, if you can't find any solution that satisfies any vector x, such that ax equal b, if you can't find any such x, we say the system is inconsistent. And now the set of all solutions is what we call the solution set. Okay, so the solution set might be empty. If the solution set is empty, it's inconsistent. There's no solution. The solution set might be one vector. Maybe this system only has one solution. Or the solution set might be an infinite set. Okay, you have infinite elements. In that case, there are infinite solutions to this guy. So what are some examples of this? So if we consider the system, so this is your matrix A, this is X, and this is B, right? So you see the system is homogeneous. Right, so this is A, this is X, this is B. And since B is equal to 0, this system is homogeneous, right? So let's try to solve this system. So we'll see later on how to solve it using matrix method, but for now, just multiply it out and let's solve it. So you got 1 by x1 plus 2 by x2 equals 0. And minus 1 by x1 plus 1 by x2 equals 0. Right, so this is equation 1. This is equation 2. Solve those simultaneously and you get x1 equal x2 is equal to 0. So the solution set has only one vector, 0, 0. So only one vector satisfies this equation here, this matrix equation. Only one solution to it. Okay. What about this system? So again, Ax equals 0. Sorry, Ax equals B, where B is 0. So again, this is a homogeneous system. Okay, because B is equal to 0. So again, do the matrix multiplication. So 1 x1 plus 2x2 equals 0. So x1 plus 2x2 equals 0. And 2x1 plus 4x2 equals 0. 2. So I'm just doing matrix multiplication there. But notice if you take this equation and you multiply it by 2, you get the second equation. So it's actually just only one equation we technically have, right? So we can ignore this guy. And when you solve it, we get x1 equal minus 2x2. So we really have two unknowns and one equation. So we could choose either x1 or x2 to be a free variable. So if I say, for example, let me choose x2 to be some free variable, let me call him a, where a is any real number. Then as I vary a, for example, if I take a, which is x2 to be equal to 1, then, and I plug it into here, then x1 is minus 2. Hence, minus 2, 1 transpose is a solution. And it's easy to see that for any a by minus 2, 1 transpose is also a solution, right? So if I say if I let x2 be some free variable a, then x1 is equal to minus 2 times a. Therefore, the solution vector is x1, x2. What is x1? Minus 2a. What is x2? A. Pull a out. So a into minus 2, 1. So equal a into minus 2, 1 transpose. Right? So that's how they got that. So any multiple of minus 2, 1 is also a solution. Therefore, the solution set is the set of all multiples of this vector, minus 2, 1, will satisfy this equation. Okay, so if a equals 0, then 0 by minus 2, 1 transpose, which is 0, 0 transpose, is a solution. If a is equal to pi, then pi by minus 2, 1 transpose, which is minus 2 pi pi transpose, is a solution, and so on. Any value of a you take is a solution. So we saw up here one homogeneous system that had only one solution. Now we see another homogeneous system that have, how many solutions are these? These are infinite solutions. Okay, so we can have one solution, we can have infinite solution. So we need a sort of systematic way to figure out what is the solution, how to systematically derive the solution set. Okay, and that gives rise to what is known as elementary row operation. So if you're wondering, is this the same elementary row operation you did in high school? The answer is yes, it's exactly the same. So the strategy for solving ax equal b is to first convert it into an equivalent system. So we will meet later on what this means, equivalent system. Cy equal d, which is hopefully easier to solve. So we have ax equal b, and this might be very complicated looking, right? We don't know how to solve it. We're going to convert it into cy equal d, and hopefully this is much easier to solve. Now this new system, cy equal d, will only be useful if it has the same solution set as the original system. Otherwise, we are solving a completely different problem. So we're now going to discuss a method by which we do this. So what is our target? We start by wanting to solve ax equal b, where a might be some complicated looking matrix that is difficult to solve. We want to convert it into another system, cy equals d, that is easier to solve. But we want to do this in a way that preserves the solution set. The solution set of the new system, I want to be the same as the solution set of the original system. Have you ever wondered why, when they were teaching you elementary row operations, why it was those specific row operations you were allowed to do? So this is what I mean. So these are the elementary operation that your high school teacher told you about. If you take a matrix A, it doesn't have to be square, by the way. None of the matrices right now for us do not have to be square. M by N matrix, we define elementary row operations. They come in three different flavors, right? The first one, strawberry, is we are allowed to interchange any two rows. And we write it like this, row I interchange with row J. So we switch it. So switch those two rows. The next flavor, chocolate, we can multiply any row by some scalar that is different from 0. So we write that as row I goes to some scalar times row I. And the last one, vanilla. So this one is maybe the least vanilla of them, of these three. We could replace any row by that row plus some constant times another row. So we replace any row by that row plus some multiple of another row. But this multiple can be 0. Otherwise, it's just this one. And we write this as row I goes to row I plus some multiple times row J. So this hopefully rings a bell. This is the same three elementary operation that you all will have most likely encountered. Why is it only these three? Or where did they even get these three operations for? Right? So that's given by this definition. So we just go through this one and stop there. So two matrices A and C are equivalent, and we write it like this, A is equivalent to C, if I could obtain C from A by performing a finite number of elementary row operations. So take a matrix A, do a couple of those row operations, any one of them, any combination, and you get another matrix C. Then we say these two are equivalent. Now the system, AX equal B. So now this is a system. So we're moving from a matrix to a system of linear equations. We are going to convert this system into an augmented matrix. So the augmented matrix means, you see the X here, forget him. We don't need the X here. We're just going to look at A and the column B. And we're going to stick those two together and we'll form this matrix, this block matrix. This block matrix is called the augmented matrix. Okay, let me draw what this thing is, right? So this block matrix looks like this. So you have the original matrix A over here, and sometimes you all do like a dotted line. If you want, you could do a straight line, and then you put the column vector here B. So over here is the original matrix, and you just add on the vector B. This is called the augmented matrix. Now, we say that the systems AX equal B and CY equal D are equivalent if their augmented matrices are equivalent. That means take this system, form the block matrix, the augmented matrix AB, take this system, form its augmented matrix CD. If it is possible to go from this system to this system by performing a finite number of elementary row operations, then we say that these two systems are equivalent. Why is this important? Because we will prove next time that if your systems are equivalent, they have the same solution. So the reason why your high school teacher only told you to use those three elementary row operations is because those are precisely the row operations that preserve the solution. If you try to do any other type of row operations, you will mess up these solutions, right? Those three operations preserve the solutions when going from one system to another. I put here as a note that equivalent matrices are an equivalence relation on the set of matrices, right? So equivalent matrices, what does it mean? It simply means you can move back and forth between them by performing elementary operations. So every matrix is equivalent to itself. You perform no row operation. If a matrix A is equivalent to a matrix B, then you could show B is equivalent to A, because if A is equivalent to B, then you could perform some elementary operation to get to B. So how to go from B to A? You just reverse the operation you did. So if you switch two rows, switch them back. If you multiplied one row by 5, multiply that row by 1/5. So you just undo the operation. And if A is equivalent to B and B is equivalent to C, that means A is equivalent to C, because to go from A to B, you perform a finite number of row operations. To go from B to C, you perform a finite number of row operations. So let's say you perform 4 elementary operations here, and let's say you perform 10 elementary operations here. So how do you go from A to C? You just perform these 4, then perform these 10. So you perform 14 operations, right? So very easy to prove it's an equivalence relation. So reflexive, symmetric, transitive. Okay, so I think that's enough for today. So we'll stop there. Are there any questions? Anything you want to ask? Feel free to